because of course that's what we're doing, we're moving into the future. It then gets interesting because you say, well, why do we have to go into the future? Why can't I stop going into the future? Well, you can vary the rate at which you go into the future relative to someone else. For example, if I was to get in a rocket now and accelerate off, even at 1g, right, just a sort of acceleration I could take, and head off and end up traveling relatively close to the speed of light, and let's say go to the Andromeda Galaxy, and then, which is 2 million light years away from the perspective of the Earth, and then turn around and come back again. If I go close enough to the speed of light, I could arrange it so I would age, let's say, a year on the outward journey and a year on the inward journey, and you could do that calculation. But 4 million years would have passed on Earth, so I would come back on that journey 2 years older, but I'd arrive at the Earth 4 million years in the future. So that's special relativity. That's Einstein's theory published in 1905, not even the theory of gravity. So time travel is possible into the future, and it's inevitable that you travel into the future, and you can vary the rate you go into the future relative to someone else by the way that you travel around. In the past, Einstein's special theory of relativity from E equals mc squared, that thing in 1905, says no, you can't, because of the geometry of space and time themselves. His general theory of relativity, where space and time can be curved, that's his theory of gravity. The correct thing to say is that we can imagine distortion, geometries is the best way to say it. We can imagine geometries of space and time. Wormholes would be an example, where if you could go through them, you could travel into the past. However, we don't understand enough. So you can calculate these things, but whether or not they're possible to make is an open question. Most people think not. And the last thing I'll say, Stephen Hawking wrote a very famous paper called the chronology protection conjecture, and conjecture is important. So he conjectured that whatever the ultimate laws of quantum gravity are, they will be such that you can't build time machines that you can use to travel into the past. Favourite fact about the universe, it's the size of the universe. The bit we can see, which is what's called the observable universe, has about between 1 and 2 trillion galaxies in it. You know, little tiny galaxies and big galaxies, but it's let's say 1 trillion-ish, something like that. And that is only a small patch of the universe that exists, so we're sure of that. Whether the universe is infinite in all directions, we don't actually know, but as far as we can tell, it could be. So my favourite fact about the universe is that it might be infinitely big. What's going to wipe out humans first? If I was to guess, I would say human, and that's not supposed to be a joke. I think that the biggest threat to our civilization is us. Beyond that, threats from space. If a comet came in from the outer solar system, as they do, it happened to hit Earth, then there's nothing we could do about it at the moment. Most of the asteroids, the big asteroids that cross the Earth's orbit, we've mapped. We're actively trying to do that. If we see that one of those big asteroids might collide in the future, then we've got a bit of time, 10, 20 years, whatever it is, so we might be able to do something about it. We're going to have to leave the Earth at some point and spread out into the solar system and beyond. If we manage to do that, and we're at the point now where we're just about to start, I hope. We're not far off being able to travel, build moon bases and then travel to Mars. We're quite a long way off going from Mars beyond the solar system, maybe. We're a long way off doing that. But at some point, if we do that, then nothing's going to wipe us out. Back in 1905, Einstein realised that space and time are not separate, but they're woven together into something that's often called the fabric of the universe, or more technically, space-time. But we now suspect, or at least we have a theory, that space-time emerges from something deeper, which is just basically quantum entanglement. So we think that there is a description of our universe which is just bits of information, basically, or qubits to be more technical, that are entangled together into some sort of network, so space and time don't exist in that network, and then space and time emerge from that deeper theory. This is cutting-edge physics, but it's one of the pictures that we have for what space and time might be. Einstein didn't begin with some grand vision. A predicting or trying to work out with a pen and paper that the universe had an origin. He wasn't interested in cosmology, really. He was interested in the behaviour. He wanted to know why things fall at the same rate in a gravitational field. And it's one of the most remarkable feats of the human intellect, but also a quite remarkable demonstration of the power of science, that thinking about that behaviour leads you to a framework to speak of the origin of the universe itself. Predicted it. About 2 years later, Edwin Hubble showed that you look at galaxies, distant galaxies, and they're all receding from us. And the more distant they are, the faster they appear to be receding. And that's the signature of an expanding universe. That was 2 or 3 years after the prediction from Einstein's theory. There's the power of science and the power of abstract thought. The genius of Einstein was to realise what we all see now. If you look at the International Space Station and the astronauts floating in it, we're quite familiar with the fact that although those astronauts can be described as being in free fall, freely falling towards the Earth, it looks for all the world as if no forces are acting on the astronauts at all. So if an astronaut gets a cup of water and lets go of it, then it just stays there. It gets a feather and puts it there, and it stays there. It gets a big 1 kilogram mass and puts it there, and it stays there. So the thing that Einstein noticed, that all things fall at the same rate in a gravitational field. If you remove air resistance, so you drop a feather and a hammer, they would fall at the same rate. That's central to the behaviour of gravity. Newton's theory works, but it's rather convoluted. There's no real explanation of that. But Einstein's theory, the explanation is that they're not falling. It is the ground that is accelerating up. There isn't really a force of gravity at all. What there is the curvature of space and time, the bending or curvature of space and time by mass. Why does the Earth orbit the Sun, according to Einstein? Because the Sun curves space and time in such a way that the straight line, the path of falling essentially around the Sun, is actually an orbit. And you might say, well, how is it? How could you replace a force with geometry? Imagine standing with your friend at the equator and you agree to walk due north. So you set off. Now, the parallel lines on the surface of the Earth are lines of longitude. So what you find is you get closer to your friend as you head to the North Pole. And so if you didn't know that you were moving on a curved surface, you would conclude there was a force of attraction between you, pulling you together, because you were minding your own business, trying to walk parallel to your friend, but you kept getting closer. You get closer because you're on a curved surface. And that's exactly the way that Einstein's theory works. If you put a sun there, a big blob of mass, it tells you what happens to space and time, how it curves. So in a sense, tells you the story or the history and future of a solar system. And that worked very well. So Einstein said, okay, well, therefore, could I not apply this to a universe? If I knew the matter distribution of the entire universe, would my theory tell me the history, the past, present, and future of the universe in the same way that it allows me to predict the orbit of planets, so the position of a planet at some point in the future? So what Einstein and a Belgian priest, actually, called Georges Lemaitre, would say, we'll make the simplest assumption, which is that it's uniformly distributed on large scales. So in that direction and that direction, that everywhere you look, it's roughly speaking the same. What does the theory tell me? And the theory tells you that the universe is either expanding or contracting. In other words, it tells you that there was an origin, because if you've got an expanding universe today, it means it was smaller in the past. So the theory actually predicted the Big Bang, the origin of the universe. We asked an amateur astronomer to take pictures of the planet Neptune, and he took photographs of the planet Neptune on 4 nights over a month. I think it was the only 4 nights when it wasn't raining in Manchester, and you see it move. It moves across the sky relative to the background, except it doesn't, of course, because Neptune's orbit is about 170 years. Neptune itself is not moving very much. What's happening is that the Earth is moving around the Sun. So what you're getting is what's called a parallax measurement. So it is exactly holding your thumb up in front of your eyes and winking like that, and you see your thumb moves against the distant background. And if you really want to, and you know the distance between your eyes, you can measure the length of your arm using parallax. So if you know the radius of the Earth's orbit, so you know how far the Earth has moved over a month, a 12th of it, then you can see how far Neptune moves, and you can work out the distance to it. And this is how all distance measures in astronomy are calibrated. Until the mid-1920s, we didn't know whether there were other galaxies. We didn't know whether things like the Andromeda. The strategy for looking for life beyond Earth in the solar solar system is based on that idea that if you go to places where there was or still is liquid water, and you go to places where there's geological activity, and you go to places where the right chemistry exists. And so that would be Mars in the past, perhaps Jupiter's moon Europa now, perhaps Saturn's moon Enceladus, and that's all we can do ultimately. So I wouldn't be surprised to answer your some kind of life on those moons, or perhaps subsurface on Mars. I would be extremely surprised if it was complex life, by which I mean multicellular life. And that's based on the fact that we have no evidence of multicellular life on Earth. But back further than, let's say, 1 billion years at most, actually maybe 600 or 700 million. So the evidence from Earth is that life remains simple for something like 3 billion years. Microbes might be common in the solar system. Complex life, it would be very surprising indeed if we found that. Is there life beyond Earth? Most people would say, well, there has to be, because the universe is so vast and so old and there are so many stars. But actually finding it is something that might happen in the next few years, let's say the next decade. Because we have space missions out there. We have a mission called Mars Sample Return, which is based on the Perseverance rover's samples that it has now collected on the surface of Mars. And we want to get them back to Earth to see if there's any traces that life may have existed or may still exist. There are 2 missions, one on the way and one about to launch to Jupiter's moon Europa, which are missions aimed at trying to find out whether that place is potentially a home for life. So I think the question, it's one of the big questions, are we alone in the universe? Of course, you can never say, yes, we're alone. But we might be able to say definitively, no, there is life beyond Earth in the next decade or so. I would say, by the way, that if we find life elsewhere in the solar system, it will be at best microbes. How many civilizations are there in a typical galaxy? And of course, the answer is we don't know. However, we can make some guess. My conclusion is there might be very few intelligent civilizations in a galaxy. I asked a great friend of mine, actually, Sean Carroll, who you might know, the author and cosmologist, on average, how many civilizations are there in a typical galaxy? And he said, none, on the average.
But do you believe that we ever find bacteria in our galaxy?
I would not be surprised at all. Well, what do we know? What evidence do we have? How can we speculate about these things? Well, we know we have good evidence that life was present on Earth around 3.8 billion years ago, which is interesting in itself because that's pretty close to the age of the Earth. So on this planet, as soon as the Earth had formed 4.5 billion years ago, it cooled down, the oceans formed on the surface. Not so long after that, we have evidence that life was present. So that's the observation that we have. So that might suggest that if you have the right conditions, geological conditions, then what kind of a thing is the origin of life? It's a transition from geochemistry to biochemistry. Whatever it is, you have a geologically active world and then you have a biologically active world. So given the right geology, perhaps it's not so unlikely that life begins. That's all. That's what you can say from the evidence on Earth.
How do you define the term time?
It's an absolutely superb question. The answer is that this is a current area of research. We don't know what time is. So in Einstein's theory of relativity, which is our best theory of space and time, we have a picture of space and time woven together into what's often called the fabric of the universe. It's called space-time. And there's a notion of distances on that surface. And they're measured by clocks. So a clock is measuring it. Let's say you have a perfect stopwatch that you start the moment you're born and you keep it with you for your whole life and you look at it now. Then that's measured your age. It's also, in Einstein's theory, measured the distance you have traveled over space-time during your life. That's fine, but it assumes there's such a thing as a clock, right? So the age of the universe, by the way, is defined as the time that would be measured on a freely falling clock that had started ticking at the Big Bang, and you had a look at it now. So a clock that just falls freely through the universe. So that's but it still doesn't say what time is. So you will see discussions in the textbooks and online of something deeply hidden, which is the deep structure of nature. but it applies across all disciplines. Something deeply hidden. That's what everyone's looking for.
What's the best piece of advice you've ever received and why?
I think it probably was during my time as an undergraduate and postgraduate when it was to just don't beat yourself up if you can't understand something, but don't stop. Just keep going. Go at your own pace. We've spoken about that a few times, actually. Just go at your own pace and just trust that if you keep going, then at some point you'll understand it. And I think that's very good advice.
Love that. And the final message for the people that have listened to this conversation today, which has been fascinating. What would you love to leave ringing in their ears? We term it your one golden rule for a high-performance life. It's persistence, I think. Given luck that we've spoken about. Where, if you really want to get good at something, then be persistent. Love it. Thank you so much.
The galaxy, these misty patches on the sky, were just gas clouds or nebula in our own galaxy. It was Edwin Hubble who showed in 1923 that, in fact, the Andromeda Galaxy is a galaxy beyond our own. We now know it's 2.5 million light years away. He did that ultimately there's a thing called the distance ladder in astronomy, which is very clever. So it relied initially on these early measurements of the Earth's radius. And then an American astronomer called Henrietta Leavitt noticed there's a particular kind of star called a Cepheid variable star that have the property that they vary in brightness very regularly, and the period of variation of their brightness is related to their actual brightness. Once you can see these stars, once you know how bright something is and you know how bright it looks, you know how far away it is. And what Hubble did was find one of these in the Andromeda Galaxy, and he found it, so he knew how bright it should be, and he knew how bright it looked, and he immediately knew that the Andromeda Galaxy was way beyond the Milky Way.
There's only one way to look into the wider universe from Earth, certainly the universe beyond our solar system, and that's to gather the light from distant stars and planets. And there is an immense amount of information contained within that light. Many years ago now, stretching back to Newton, and even before, we looked at the light from the sun, and after Newton we found a way of analysing it by splitting it up into its component colours with a prism, essentially making a rainbow of the light from the sun, just as nature makes a rainbow of sunlight using water droplets. But when you look at the light from the sun in a laboratory and you're very careful and you put it through a very precise prism, then you see that it's not just an array of colours, it has dark lines in it. All these black lines crisscrossing the rainbow. What those lines are the signatures, the thumbprints, the chemical elements themselves. An element is a nucleus with electrons going around it, and each element has a different nucleus and a different arrangement of electrons. What happens with the light from stars is that the light shines through elements in the star's atmosphere, so elements like hydrogen and oxygen and helium. And because those elements have different structures of electrons around their nucleus, they absorb different colours of light, very specific colours that correspond to moving the electrons around in very specific ways. For example, these two lines here are very famous. They're called the sodium lines. Sodium absorbs light in the yellow part of the spectrum. If you heat sodium up, it emits light in the yellow part of the spectrum. So what you're seeing here is the signature, the fingerprints of elements in the sun. That's interesting in itself because you can immediately read off what the sun's made of, because you can do an experiment on Earth, see which colours the elements absorb or emit, and you can look in the starlight. You can see what the stars are made of. Light travels at 300,000 kilometres per second, 186,000 miles a second. And at that speed, it's taken over 13 billion years to travel from the most distant object in that image to Earth to the Hubble Space Telescope. Now, when you think that the Earth is only just under 5 billion years old, it means that most of the light from most of the galaxies in that image began its journey to Earth before there was an Earth. And for some of the most distant galaxies there, they were over halfway here when the solar system was just a cloud of gas and dust. It hadn't yet coalesced into the sun and the planets and moons of the solar system. Imagine what that looks like when you extend it over the entire sky. Well, this is a beautiful map of the observable universe. Every dot on that map is a galaxy with 100 billion stars like our sun in it, at least. There's a ridiculous number that I have to show you. It's better to show it than say it. This is the number of stars in the observable universe at the moment. 30,000 million stars, just like our sun, some bigger, some smaller. 350 billion large galaxies, 7,000 billion smaller dwarf galaxies. That's the observable bit of the universe. We have pretty strong evidence now the universe is significantly bigger than that, but we can just see this blob surrounding us, the blob from which light has had chance to travel during the history of the universe. I don't know if you know a comedian called Woody Allen. He once said that the universe is probably infinite, which is a bad thing if you're one of those people who can't remember where they put things. The universe is expanding. So if you look at a very distant galaxy, then you find all the distant galaxies are rushing away from us. Think about what that does to the light. What happens to the light is the light begins its journey from the distant galaxy. Light is a wave. You just imagine a wave on its journey through space. The space is stretching because the universe is expanding as the light journeys from the distant galaxies to us. So the wavelength of the light is stretched. The wavelength is the colour. Red light has got a bigger wavelength than blue light. So as the light, let's say there's an element down here that emits